Hey everyone, welcome to InsightsByRish. In today's video, we are going to implement a project of flower images classification in which we have various flower categories and we are going to classify them accordingly. Now, this is also a deep learning project with a transfer learning approach where we use the pre-trained models for image classification. Now, the new addition in this video is we are going to make use of data augmentation techniques here. In my previous two image classification videos, I haven't used any kind of data augmentation technique. And in this video, we are going to use that. And also here we are going to make use of EfficientNet Transfer Learning approach. Now for this, I'm going to make use of this flowers dataset from Kaggle. I will provide the link of this dataset in the description box. In this dataset, we have various files from which we are going to make use of this train folder, in which we have another 5 folders consisting of various flower classes like daisy, dandelion, rose, sunflower and tulip. Now we have to classify the flowers accordingly into one of these 5 categories. So going back to the code, the first task that we have to do here is loading the dataset. Now we are going to make use of API token for loading the dataset here in the Google Colab directly. The another approach here is either you can download this dataset into your system and then you can upload that folder here in your Google Colab environment. But the simplest way here is just create an API token, and with the help of that you can extract all the data here in the Google Colab. So what you have to do, go to your Kaggle, click on your profile and go to settings. When you go to settings, you will get an option of create API token. Once you scroll down, just click on that, and once you click on that, kaggle.json file will be downloaded in your system. Then you have to place that kaggle.json file here in your Google Colab environment, as I have already done. And with the help of this file, you can directly connect this Google Colab file with that dataset and directly extract the data from there. So let's start. Now starting with, as we have this kaggle.json file in our environment, it's also necessary to validate this file. It's also necessary to identify this file, and we are going to write the code to identify this file first. So let's say mkdir and then -p and then the name of your file, that is Kaggle. Then again exclamation cp, and then you have to give the name of your file with extension. So kaggle.json, and the same thing what you wrote previously, that is .kaggle. Now this code will basically identify that we have some kind of kaggle.json file in our environment, and only when it is identified we can move ahead. So let's run that. Now as you can see, the file has been identified. Now moving ahead, we have to extract the data here in the Google Colab. So what we have to do, let me just close this. Going back to the dataset, we have to copy API token from here. As you can see here, we have a option of copy API command. So we just have to click on that and a API command will be copied. You have to place that command here, and don't forget to precede it with an exclamation mark. It's very necessary to put this exclamation mark in the beginning of API command. So let's run that. Now as you can see, it's downloading the data, and you can find one zip file here which is getting downloaded in your Google Colab environment directly. So the downloading has been successful and the file has been downloaded here in your Google Colab environment. But the issue here is it's in zip format, so it's necessary to extract the zip contents, and for that we are going to write a code here. So let me write here, first we have to import the library for that. So let me write here importing libraries, and we will import all the libraries in this particular cell as per our requirement whenever necessary. So the first library that we require is to extract the zip contents, which is import zip file. Let's run that. And here we are going to write a code to extract the contents from zip file. So let me create a zip reference, and here I will say zip file, that is the imported module, and then the zip file. Now here we have to place the path of our zip file. So just copy the path and place it here. After that, the next thing is we again have to say zip reference dot extract all. Here you are going to extract all the contents. Now first, this path is from where you are going to extract the contents, and here you have to give a path where you are going to store that extracted contents. Now again, we are going to store all this extracted contents in this Google Colab environment itself, and hence I am going to give the path as content. Content is where all these folders have been saved. And after that you have to close that zip reference here. So zip reference dot close. Let me run this. After running that, when you refresh your environment, you can see that now you have multiple files and folders downloaded from the Kaggle directly here in your Google Colab itself. And from this, we are going to make use of this train folder. So let's rename this train folder to something different. Let's name it as flowers. Now, after renaming, the next thing that you have to do here is you want to create the base directories and the categories. So let's name your base directory, that is the base folder in which you have all other folders. So let's name it as data directory, that is data dir, and here you have to place the path of your base directory, which is flowers. So just copy the path of flowers directory and place it here. After that, you have to give the categories here, the multiple categories that are available in this flowers folder. So the categories should be in the same sequence as they are in this flowers folder. Like in the flowers folder, the first folder is for daisy, followed by dandelion, and then rose. In the same sequence, we should also put the names here. So the first one is daisy, and also the spelling should be exactly same for both in the flowers folder and in this categories list. Then the dandelion, then rose, then sunflower, and the last one is tulip. So the first, let me also put a comment here. This is our base directory. So later what we are going to do when we are constructing the path, there we are going to append this single individual categories with this base directory to extract the data from that particular folder. So let's run this. After doing this, we are done with the first agenda of this project, which is loading the dataset. After that, the second thing that we have to do here is visualizing the images. Now to visualize the images, as we have 5 folders here in our base directory, we are going to display 3 random images from every folder. That is 3 random images from daisy folder, 3 random images from dandelion folder, and like from every folder, we are just going to display any 3 random images. So we'll write a code for that. So let's say here, visualizing the images. So for category and categories, so this category in lowercase is going to extract individual elements from this uppercase categories list, and here we are going to construct the path. So let me say constructing the path. The path will be, now here we will require a module named as OS. So let me import that as well. Let's run that. And we are going to make use of that module here. So let me say os.path.join. Now what we are going to join is our base directory that we created, that is data directory, with every individual element from the categories list. So category. Like for first iteration, this lowercase category will contain the value daisy, and that will be concatenated or appended with the base directory to enter the daisy folder. In the second iteration, the lowercase category will have the value dandelion from the uppercase categories list, and that will be appended to the base directory path, which will eventually enter the dandelion folder. So this is how we are basically going to construct the path. Now you will create a variable called as images, and here you will say os.list directory, and you will pass that path here. After that, now we will build a subplot. Subplot basically means it will consist of multiple images, which is visualized with the help of matplotlib library. So we will also require matplotlib here. Let me import that. So import matplotlib.pyplot as plt. Let's run that. So what I will do here is, let me say figure comma axis is equal to plt.subplots, and here we will have the value 1, 3, which means in every single row we want 3 images. Like for every folder or for every category, we want 3 random images. So this basically specifies that for every row, that is in every single individual row, we want 3 columns. After that, we will also give the figure size here inside this parenthesis only, which is a fixed size, and let the size be something like 10,4. After that, we also have to give the title for every subplot. So let me say figure dot subtitle. It's actually SUP, subtitle. And here you have to name your subplots. Now, one thing we can do, either we can give these titles manually, or the simplest thing that we can do here is we will just pass this lowercase category here, so that whatever element is getting extracted from this categories list will be given as a title here. So let me say category, and we'll also give the font size here. So let the font size of the title be 18. After that, we will write a for loop here to display the images. So for I in range 3, as we want to display 3 images, so 0, 1 and 2. Then we will say image name is images, and as we want to display the random images, we also require numpy here. So let me also import that. Import numpy as np. Let's run that. And here we will make use of random module from numpy to display random images. So numpy.random integer. Now we also have to give the range from which the random images should be extracted. Like if we have 1000 images, so the range should be 1000. Now from that 1000 images, any 3 random images will be extracted. So the range will be starting from 0 up till the end of images that we have in the folder. So we will say length of images. So 0 is the starting point, and length of images, so whatever the length of images will be, that will be ending point, and from that length or from that range, any 3 random images will be extracted and displayed here. After that, we will say image path is equal to os.path.join. Then we are going to join the path that we created here, and then the image name. After that, we will read that array or the image data. So let me store it in a variable called as image array, and here I will say CV2. Again, we require the CV2 module as well. So let me also import that. Import CV2. Let's run that. And here I am going to make use of CV2 module to read the image data. So I am read the image path. After that, to display the image, we will say access at the location I am show the image. And here we will switch off the x-axis and y-axis, as we don't want any kind of axis to be displayed. We just want the image. So the axis is off. And let's run that. Now, as you can see, it's displaying 3 random images from the available categories. So these are the 5 categories that we have: daisy, dandelion, rose, sunflower and tulip. Now one thing you can notice here, that every image is in a kind of blue color. Like every image has a slightly blue tint, and the issue arises because the matplotlib requires the images in the RGB format. To display the images, matplotlib library basically requires the images in RGB format, red, green and blue. But the CV2 module that we are using here to read the image data takes the images in exactly the opposite format, that is BGR, blue, green, red. So matplotlib requires images in RGB format, but CV2 is reading the images in BGR format. And hence the necessary step here is to convert these images from BGR format to RGB format, so that the matplotlib can read it correctly. So the step here is converting the BGR, that is blue, green, red images, to RGB, that is red, green and blue. So we will say image underscore RGB is equal to, again we will make use of CV2 here, and we will say convert color. And here we will pass our previous array, which is image array, and we will convert the color to BGR. So we will make use of BGR to RGB. So we are basically converting the images that's the CV2 module is taking in BGR format to RGB ones, and then we will pass this image underscore RGB variable here in the IMShow method, and let's run that. Now, as you can see, now it's displaying you the color images. So you can see now it's showing you the color images from every available category, and this is what you wanted. So we are done with visualizing the images. We displayed the images from every available folder, that is all the 5 folders. So the next and the most important thing that we are going to do here is data augmentation. Now by data augmentation, what I mean is, let me take you to Google here, and here this image of data augmentation is from Medium. As you can see, this image is of butterfly, and the image on the left hand, that is a single image, is an original image. And after data augmentation, we are converting that single image into multiple formats. We are shifting the image, we are rotating the image, we are decolorizing the image, we are contrasting the image, we are flipping the image vertically and horizontally. So basically we want to make our model very efficient, and we want, no matter the image is in what format, the model should efficiently classify the image. And for that we are changing the format of images here. We want that if in case if someone gives an input of tilted or rotated or decolorized image to our model should be able to identify that image as well. And for that we make use of data augmentation, because if we train our model only on the pre-processed and very formal structure of images, then in that case, if by chance someone gives messed up images to the model won't be able to classify them. And for that we make use of data augmentation here. So we are going to basically do this all stuff there. We are going to decolorize our image, we are going to increase the contrast of our image, we are going to rotate the images horizontally and vertically as well, and all these things. We are also going to crop the images. We just want some portion of the images as well, by using which the model can able to classify the images as well. So we are going to do all these things there, and for that we are going to make use of image augmentation library. So from image augmentation we are going to import augmenters as, let's give an alias of AAA. Let's run that. So after doing that, now once you perform data augmentation, the number of images in your folders will be increased, and only by that way we can verify whether the data augmentation has been happened or not. As you know, if this data augmentation will be applied on every single image, that is for every single image all these copies will be created. One, we will have original image, and then after that original image we will have the decolorized image, the enhanced image, the rotated image. So this will be applied to every single image available in every single folder, and hence the count of images in every folder will be increased. And data augmentation has been happened or not can be only verified after checking the count of images in every folder after performing data augmentation. And for that we will write a code here which counts the number of images in every folder. So we will check the count of images first before performing data augmentation, and after performing data augmentation to verify whether the augmentation has been happened or not. So here I will say def count images. So this function will basically count the images in every folder, that is the count of images in daisy folder, the count of images in dandelion folder, and all those stuff. And then we will pass our directory here, which will be our base directory. Then for category and categories, and then the same thing that we did previously, we will construct the path here. So we will say os.path.join, and we will join the directory. The directory is the one that we are receiving in this function, and we will join that with every individual category, the same thing that we did previously. And after that we will say images is equal to os.list directory, and here we will pass that path. After that we will say number of images is equal to the length of images. Now this images, length of images, this images variable is having all the images from particular folder. Like for first iteration, this images variable will have all the images from the first available directory, which is daisy, and it will count the length of that images. After that, in the second iteration, this images variable will have all the images from the second available directory, which is dandelion, and here it will count the number of images present in that particular folder. And after that we will say print. Here we will also print the category to analyze the number of images from what category. And then here we will say number of images and images. Then we will call this function here itself. We will call it as count images, and here we will pass our data directory. So data directory. Let's run that. As you can see, this is the original count. Originally you have 501 images in daisy folder, then 646 images in dandelion folder, and all those stuff. Now we have to verify that after performing data augmentation, whether this count of images increases or not. If it increases, that means data augmentation has been successfully applied, and if it don't increase, then that means the data augmentation has been failed. So here we'll say data augmentation, and I will say augmentation, a short form for that, AUG. And then IA, this is an alias for the module that we imported from image augmentation. Then sequential. Now first we are going to perform horizontal flip. So let me write here horizontal flips. So I will say IAA, and then I will make use of built-in method which is flip LR. Now you have two methods here. As we are flipping it horizontally, hence we are making use of flip LR method, that is flip left right. If you want to flip it vertically, then you can make use of flip UD method, that is flip up and down. And then we will give the value here by what measure you want to flip that image, that is 50%. And after that we are randomly going to crop the images. So randomly cropping images. Up to 10% of its size. So you can crop it up to any percent of its size. Let me keep it as 10%. And then we will say IAA.crop, and we will give the percent by which we are going to crop the image. So the percent is 10%. So 10% of the original size, hence 0,1. 0.1 represents 10%. Now after cropping and flipping, the next thing that we want to do is we want to scale the image between any percent of its size, and we also want to rotate it. So let's say that we want to scale the images by 80% and 120%, and also we want to rotate it between -25 to 25. So let's say scaling the image between 80% and 120%, and rotating it between -25 actually, so -25 to +25. So here we will say IAA dot, we will make use of affine that does both the work of scaling and rotating, and we will say scale is equal to, as it is 80% and 120%, hence we will keep it as 0.8 and 1.2. and after that we will also give the rotate parameter here. Let's say -25 to +25. So this was for scaling the image and rotating the image. After that, the next thing that we want to do is changing the brightness of image. So let's say here changing the brightness of the image. So we will say IAA.multiply, and you can change the brightness by any measure. Let it be the same as previous one, that is 80% and 120%, so 0.8 and 1.2. And after that, the last thing that we are going to do here is adjusting the contrast of the images. So let's say IAA, and we are going to adjust this contrast linearly. You can do other ways as well. So let me say linear contrast. So let's give the value as 0.75 and 1.5. You can change the values as well. So these are some things that we are going to do to our images. We are going to flip the image, every single image. Then we are going to crop the image up to 10% of its size. We are going to scale them, rotate them, change its brightness, and adjust the contrast as well. You can even do more things here. You can here we have just flipped it horizontally. You can even flip it vertically. Then you can crop it to some more different size. You can make it grayscale, and you can do much more things here. And I have missed some commas here. Fine. Now this is the code that we have written for the augmentation. We have to create a function now, and we have to apply this code on every single image that we have in our every single folder to perform data augmentation for every image. So let me write a code here. I will write it here itself. So let me say def augment images, and here I will pass the directory and this augmentation that we created here. I am also going to pass that here in this function. After that, the same thing that we written previously, that for category in categories. After that, we'll again construct the path. So let me copy it from here. After that, for file name in os.list directory of that path, here we will say we are going to read the image here. So image is equal to cv2 dot imread, and we'll say os.path dot join the path and file name. Now, as I said previously, we also have to convert this image into RGB format, as by default cv2 reads the images in BGR format. So the next thing is converting the image. Again, we will say image is equal to cv2 dot convert color. So I will pass this image. Now this image which we are passing in the convert color method is this previous image in which we have read the data, and we are going to store it in a new variable with the same name image. Then here we will say cv2 dot color, then BGR to RGB, and after that we are going to apply this augmentation on every image. So let me say augmented image is AUG, it is this variable, and then augment image. After that I will pass this image here. Then next thing we also have to do here is we also want to store this augmented images in the existing folder. It's actually image, not images. Just a minute. Fine. So let's say this augmentation have been applied on the images, and we have now new images which have been rotated, shifted, tilted, flipped, and all those stuff. Now all those images we also want to store them in the existing folders, like the augmented images generated for Daisy folder should get stored in this Daisy folder. The augmented images generated for rose flowers should also get stored in this rose folder. So for that we will write a code here to store these images to the existing folders, and we will say new file name is equal to os.path.join split text. We want to give some names to that images, so we will say split text, actually only a single T here, and then file name at the position 0, plus we are going to also give the word augmented for that image name, so that we can easily identify that the image was originally present in that folder or whether it is stored in the later part. So we will give a suffix here of underscore augmented os.path.split text and the file name, and then the 1. After doing that, we are going to say cv2.imwrite. We are going to write this file name to the newly created images. So os.path.join, and here I will say path comma new file name which we are going to give them, and here I am going to pass this augmented image. Now we are going to apply this function on every single image that we have. So let me say augment images, and here in this function we require two parameters to be passed, which is data directory and our categories. Actually it's not augmentation, it's the categories that we are going to give them, that is the list of categories. So let's run this. So I have misspelled here. Now this augmentation has been happened, And the next thing that we want to do is we want to verify whether these augmented images have been stored in our folders or not. Many times it happens that the augmentation happens, but the images, that is the generated images, doesn't get saved or the stored in our folders. So we'll again call that function of counting the images. I think the function name was count images. Let me call this function again. And as you can see, the count of images have been increased. Initially we had 501 images in the DAISY folder, and now we have 102. Then we had 646 images in Dandelion folder. Now we have 1292 images. In every folder, the count of images has been increased, which means the data augmentation has happened, and also the generated images have been stored in the folders, existing folders actually. After doing that, we are also done with the third agenda of this project flow, which was data augmentation. The next thing that we want to do here, now as we are we are going to go ahead with the train test split, but before doing that, the first thing that we want to do, as we are working with EfficientNet Transfer Learning model, the image size should be compulsorily be 224 by 224. It's mandatory to have our image size as 224 by 224 when we are working with EfficientNet Transfer Learning module. So when you check the image size here, let me say image array.shape. As you can see, the default size is 213 by 240, but we want it to be 224 by 224. And also for every image the size is different. As you can see, when we visualize the images, you can see the image size is different for every image. In this sunflower, the third image is small as compared to the second image. Also in the daisy folder, the first image is small as compared to the other two. So every image size is different here, and we want that every image should be of 224 by 224, and hence we are going to resize them. So let me write here resizing images. So let me give the image size as 224, and here I will say new array is equal to cv2 dot resize, and here I am going to pass the image array, that is the existing image data, and the new image size, which is image size by image size. And then let me also display that image. So this is the image. Okay, so it also has blue tint. We also need to convert it here. So let me say image is equal to cv2 dot convert color. Let me pass this new array here, and cv2 dot color BGR to RGB, and then we will pass this image here. Let's run that. So now you can see the original color of the image. Now this image has been converted to 224 by 224 dimension. If you reduce the image size to a more lower value, let's say 50, you can see there will be a lot of glitch visible in the image. Now as you can see, the image is very blurry. If you lower it to some more small value, let's say 20, you can see a lot of more mess and more blurring there. So the image size should be either 224 or less than 224 when working with EfficientNet Transfer Learning model. It cannot exceed the 224 limit here. So after doing that, let me run this again. Now we are going to create our training data. So the next thing that we are going to do here is creating training data. So here I will create an empty list in which later I will append the data. Training data is equal to empty list. Now I will write a function here. So let the function name be create training data, and in this function we will again do the same thing whatever we did previously. Now though we have images, that is we have input to our model, but we don't have target values here. We also need to classify them, so they should have some labels. And as you know, when we make use of any kind of CSV files or a supervised learning, then we have the labels along with the input, but here we don't have any kind of labels here. Hence we want to assign them manually. So let me say labels is equal to categories dot index category. So what this is doing is we are creating numeric labels here. This index method is basically extracting every single individual element from the categories list. Let's say for the first iteration it extracted the daisy folder or the daisy element. Then for that daisy element it will assign some index, and in the second iteration it will extract the dandelion element, and for that particular class it will assign a label. And here directly we are assigning the numeric labels, because here if in case you assign string labels, that is if you give the names of flowers here, then in that case later in the model building process you again have to convert them into the numeric format. Hence it's better to directly give them the numeric labels. After doing that, let's say for image in os.list directory and path. Now we are going to put this code in try catch block. So let's say try, and here we will create an image array, the same image array that we created previously as well. So let me copy it from here. The only difference is instead of this file name, here we have image. After that we will again say image array, and we also have to convert its color format from BGR to RGB here. So we will copy the same code, and here we will just pass the image array. After that we'll create our new array in which we will resize them to new size. So whatever we did here, we'll just copy it from here. And after that we are going to append this input data and the labels in the training data, this list that we created. We are going to append this new array. New array consists of all the input data of our images, and this labels consist of unique label for every category. We are going to append this input and target in our training data list. So let's say training data dot append. Here first we are going to append the new array that consists of our input data and then the labels. So this was the try block, and in the exception block, let's say except exception as E. I will just say pass. I won't write any code here, and then we will call this function. So let's say create training data. Let's run this. So the issue here, it's actually data directory here. Now the training data has been created. The next thing that we want to do, first we will check the length of our training data. So let's say length of training data. So in total this training data consists of 5492 images consisting of all those flower classes. Now we want to divide our data into input and target. We want to create an X variable and an empty Y variable, or we can say the list, empty X list and empty Y list, in which we are going to append our input and target data. Now in this empty X list we will append our input data that is stored in this new array, and in Y empty list we will append our labels which are stored in the labels variable. So here I will say for features comma label training data. Now in our training data we have two distinct features. The first one is new array, that is our input, which we are going to extract in this features variable, and later we are going to append in this X empty list. And the second distinct feature that we have there is the labels, which will be extracted here in this label variable and later will be appended in this empty Y list. So here we will say X dot append the features and Y dot append the label. Let's run that. Actually there's no parenthesis here. After doing that, when you check the type of your x and y, so let's say type of x and type of y, you can see the images or the data is in the format of list. But when you are working with any kind of transfer learning models or any kind of convolutional neural network models, it's necessary to have them in array format, and hence we will convert them into array. So let me write here x is equal to np.array, and we will also reshape them, reshape our input data. So let's say reshape -1, and then the image size by image size, which we have given as 224. And here we also have to mention our channel dimension. Now, as we are working with color images, we will give the channel dimension as 3. But if you are working with grayscale images, then you have to give the channel dimension as 1. Also, the next mandatory thing is when we are working with any kind of transfer learning models, that is the pre-trained models like VGG16 or EfficientNet, in that case you should work with color images because they are trained on color images. They cannot process the grayscale images. So we will say the next thing is y is np.array, and here we will pass our y. No need to reshape it. Let's run that. And now we will perform train test split here. So the next agenda is train test split. And for that we require train test split module from scikit-learn. So let me import it here from sklearn.model selection. We require train test split. Let's run that. So here I will say xtrain and xtest, then ytrain and ytest. Is equal to, then we will call that module here, that is train test split, and we will pass our input and target there, that is x and y. Let's give the test size as 0.2, which means 80% data in the training set and 20% data in the testing set, and then the random state. So let's run that. So let's print some data about the training and testing set. So let's say print, first we will print the length of training set. So xtrain length, let's say it's xtrain dot shape at index 0. Then we will print the xtrain image size. Now image size is 224 by 224, hence it will take 2 indexes. So it will be present on xtrain dot shape from index 1 to 3, that is index 1 and 2. And then we will take the channel dimension here. So say channel dimension will be xtrain dot shape at location 3. And we will also repeat the same thing for testing as well. So let me copy it from here, and we will just change the xtrain to xtest. So let's run this. As you can see, out of 5,492 images that we had in total in our training data, 4,393 images are in training set and 1,099 images are in the testing set. And the image size for both training and testing set is 224 by 224, and the channel dimension is also 3 for both the set. After that, now we will start building our EfficientNet model. As you can see, the next agenda that we have here is building the EfficientNet model, and for that we require a module here. So let's say from tensorflow.keras.applications, we are going to import the EfficientNet. So EfficientNet, and we have various versions of this EfficientNet. We are going to go ahead with the B0 version, and let's run that. Actually TensorFlow. After doing that, we will go back, and here we are going to build the EfficientNet model. Here we are going to say EfficientNet, and the model that we have loaded, which is EfficientNet B0. And here we will say weights. Now this model has been trained on the ImageNet dataset, and we are going to take the weights from that. So the weights is ImageNet. The second thing is include top. We don't want any kind of fully connected top layers to be included here. This is an image of EfficientNet architecture from Medium, where you have various convolutional layers and MB convolutional layers. Now the starting convolutional layer that we have, that is called a stem. It is a simple convolutional layer with some batch normalization layers. And after that, when you have this MB convolutional layers, they are the core part of this EfficientNet architecture, which is also called as mobile inverted bottleneck layers. Now I'm not going to talk much about the architecture of EfficientNet, as this video is not about the theoretical explanation about EfficientNet, but just about the implementation of that. So let us go back to the code, and here I will say input shape is, now the input shape will be the new image size that we have set, which is 224 by 224. Either you can directly give 224 by 224 here, or you can make use of this image size variable. And then the channel dimension as 3. Let's run that. It's actually weights. And it's also include top. So as you can see, these weights have been downloaded. Now after that, we are going to freeze the pre-trained layers. As you can see in this architecture, all these layers have been pre-trained, and we don't want to train them again. So we are just going to freeze them, and for that we'll write a code here. So freezing the bottom layers. So we will say for layer in EfficientNet dot layers, we are just going to say here layer dot trainable is false. Let's run that. Now we will construct the fully connected, that is the dense layers on the top of this bottom layers. So let's say here constructing the fully connected, or you can say dense layers, which are also called as top layers. So here we will say model is equal to keras.sequential. I think I haven't imported keras here, so I haven't imported it. Let me import. So first we will say import TensorFlow as TF, and then from TensorFlow I am going to import keras. Let's run that. So here I will say keras.sequential module. First we will pass our EfficientNet. It's actually EfficientNet. It should be EfficientNet. And then we will pass this EfficientNet here. That will be our first layer. After this first efficient layer, we will pass our global average pooling layer. So let me say keras dot layers dot global average pooling 2D. This is the second layer that we are passing, and then we are going to pass our dense, that is the fully connected layers, and our output layer. So let me say here keras dot layers dot dense. Now you can give any number of neurons in this dense layer. Let me give it as 1024, and then the activation function. And in every hidden layer, it's always ReLU, that is rectified linear unit. Now this is our first hidden, or you can say the first fully connected layer. You can put as many as hidden layers as you want. I will just have 2, that is this first, and then one more, and let it consist of 512 neurons. And now I will give the output layer. Now as you can see, we have 5 categories in our flowers folder. You can see we have 5 categories in this flowers folder, which is daisy, dandelion, rose, sunflower, and tulip. And as we have 5 categories here, we are going to give 5 as our output neurons. So in our output neuron, in our output layer, we will have 5 neurons, as we are having 5 classes in our base directory. And the activation function will be softmax. For multi-class classification, it's always softmax, and for binary classification, it's sigmoid. Now after constructing this model, we are going to compile it. So let me say model.compile. Now here you have to give the optimizer, which is Adam. That's currently the best available optimizer. Then the next thing is loss. Now, as we are working with multi-class classification, the loss function is categorical cross entropy, and as our target features are not one hot encoded, hence we will say sparse categorical cross entropy. So sparse categorical cross entropy. And then the metrics, that is depending upon what we are going to evaluate our model. So we are going to evaluate our model on the basis of accuracy. So this was the code for compilation, and then we are going to fit it. So model.fit xtrain, ytrain, and then the number of epochs. Now always start with less number of epochs, and then depending upon the accuracy you can later increase the size of epochs, but initially always keep the size low. So let the number of epochs be just 10, and then the batch size. As we have a lot of data, we are not going to pass it individually one by one, we are going to pass it in batches, and hence we will give the batch size as 32. You can give it anything. Now before running all this code, make sure that you are changing your runtime type here. So just go to runtime and change your runtime type to T4 GPU, because it will make your computation faster. Now as you can see here, here in the right corner, we are connected to T4 GPU, and now advantage of this is when you keep your runtime type to the default one, that is the CPU, it makes your computation very slower, and when you switch it to T4 GPU, it makes your computation very faster, especially in case of this convolutional neural networks. But the disadvantage is all the progress that you made is lost, so you have to run all these cells from starting again. So let me run all these cells again, and then we also have to again rename our train folder to flowers. So let me rename it to flowers, and then we will run all these cells again. Now as you can see, the number of epochs have been running. It's started. In the first epoch itself, you have got an accuracy of 85%, which is really good. Until the time it's running, we will write the code for loss and accuracy. So loss and accuracy is model.evaluate. Now we are going to evaluate our model on the testing set. So we'll say xtest and ytest. And then we will also print the accuracy here. So let me say print model accuracy. And as we want to display the accuracy in percentage format, hence we will multiply it by 100. Now whatever accuracy here you are seeing in the training process, that accuracy is on the training set, and when we are evaluating our model, we are actually evaluating our model on the testing set. So we want to check whether the testing accuracy and the training accuracy both are near to each other, or there is a drastic difference between both of them. If there is a drastic difference, then in that case we can call it as overfitting, and if there is a very little difference or no difference, then that model is an efficient one. So as you can see, at the end of 10th epoch, the accuracy that you are getting on the training set is 98%. So let's evaluate our model on the testing set. Let's run this. Now as you can see, we are getting a very good accuracy of 92% on our testing set as well, which means the model is performing really very good. Now if you increase the number of epochs here from 10 to let's say something 30, 50, you will get more accuracy. You will achieve more good accuracy on the training and testing set, but there also might be chances of overfitting. So we will keep it to 10 itself. After doing this, as you can see, the model is giving an accuracy of 92% on the testing set. Next, we want to make some predictions here. So let's say model.predict on xtest. Let's run this, and you can see you will get a series of predictions for every particular instance. For first instance, you are having 5 predictions or 5 probabilities of predictions, and for the second instance you are having 5 probabilities of the predictions. This is because we have used the softmax activation function in our output layer. What the softmax activation function does is it gives you the probability of every class. That is, for the first instance, it gives you the probability that image belongs to which class. Let's say in this first instance, the probability of image belonging to the first class is 3.8 e⁻⁻⁶%. For the second class, the image belonging to second class, the probability is 1.22 e⁻⁴%. For the image belonging to third class, the probability is 3.40 e⁻⁵%, and all those stuff. Then we have to extract the index at which we are having the highest probability, and that index is our true label or the predicted label. So what we will do here is we will say we are going to use numpy here, and we are going to store all these predictions in a variable called as spread. Then we will make use of that numpy library and argmax. It will extract us the index at which the maximum probability value is present. So, and we also need to reshape it. So axis is -1. Now when you display the predictions, you will see a single label there. Fine. So for the first instance, the highest probability was on the index 4. For the second instance, the highest probability was on the index 1. And hence they are the predicted labels now. Now let us compare the actual labels and the predicted labels. So let's display the first 5 true labels which are stored in whitelist. The first 5 true labels are 4, 0, 2, 1, 4, which means the label 0 has been assigned to the daisy class, the label 1 has been assigned to the dandelion class, 2 for rose, 3 for sunflower, and 4 for tulip. So in our testing data, the first flower belongs to tulip, the second flower belongs to daisy class, the third flower belongs to rose, the fourth flower belongs to dandelion, and again the last flower belongs to tulip. So let's see what our model has predicted, which is stored in the pred. So first 5 predicted values are. So as you can see, the first 5 predicted values are very slightly different from the testing values, but still the model is giving us good accuracy. If you want, you can also check it on different values. Let's say we want to check the testing set from 10 to 15. And we'll also check what our model has predicted for 10 to 15 set. As you can see, somewhere the predictions are exactly similar and somewhere there is a difference. So the next thing that we want to do is we are going to use this predicted variable and this testing variable to display the classification report and the confusion matrix. So let me import that first. So here I will say from sklearn.metrics, I will import classification report and the confusion matrix. Let's run this. And let us display the classification report here. So I will say print classification report, and here you have to pass your true labels which are stored in whitelist and the predicted labels which are stored in pred variable. So let's run this. So as you can see, this is the classification report for your model, and the F1 score for every category is good. If you find the drastic difference between the F1 score of each category, then that means the dataset is imbalanced. That is, it is having a high number of images in one category but very less number of images in other category. In that case, you have to balance your images or balance your dataset. But here the F1 score is very good for all the categories, which means this dataset is balanced. After this, we will print the confusion matrix. So we'll say CF is equal to confusion matrix, and here again we will pass the true labels which are stored in whitelist and the predicted labels which are stored in pred. Then we will say normalize is equal to true. This is because we want the data, that is the accuracy percent, and not the accuracy count. And then to plot this confusion matrix, we require cbun. So let me also import the cbun here. So import cbun as SNS. Let's run that. So here I will say sns.heatmap, and here I will pass the CF variable. Then anot is equal to true, which means basically you want to display the value on the grid of heat map, and then CMap, that is the theme of confusion matrix. So let it be blues, that is it will be a tint of blue. And on x-axis we have predicted values, hence I will also give the labels here. So x label, we have predictions, and on y label we have actual values. So y label will have actual. Let's run this. So as you can see, this is your confusion matrix. On x-axis you have the predictions, and on y-axis you have the actual values. When you take the look at the diagonal, that is the dark blue squares, they portray the accuracy for correct prediction. let's take the look at first coordinate, that is 0, 0. You can see the value is 0.94, which is 94%, which means the model is giving an accuracy of 94% while correctly predicting the class 1, which is I think it's Daisy. For the second coordinate, you can see 1, 1, the accuracy is 0.96, that is 96%. That is, the model is giving us an accuracy of 96% for the correct classification of the second class, which is dandelion. And that's how the confusion matrix is interpreted. So this was the project for flower image classification using the transfer learning approach of EfficientNet. In one of the previous video, I implemented the image classification project using VDG16 transfer learning approach, and here I have implemented the project using EfficientNet transfer learning approach. So that's it for the video. Thanks for watching.